Welcome back to H2ology. I'm Dr. Chris Anastasiou, Chief Water Quality Scientist.
And I'm Dr. Mark Fulkerson, Chief Professional Engineer. In part 2 of our 4-part series on watershed management, we're going behind the scenes of flood risk mapping and modeling.
And we're going to show you how these models are built and the science that powers them.
When we think about the rainfall events too, we will go through periods where it doesn't seem like it's raining for a decade or 2 decades. And then we'll go through periods where it seems like, wow, we're getting all these storms now. And so we have a lot of rain gauges that go back 100 years plus. And we can look at those rainfall data and we can say, okay, here's an area where it just was above average rainfall so many years in a row. The 1940s was a wet period. The 1960s, early 60s was a wet period in the late 50s. But then by 1962, it was this extreme drought, for several years. And so, with rainfall and what we've kind of studied and seen, we're looking at a snapshot in time. We can say we've got 100 years of rainfall data, but what happened 100 years before that, or what happened 500 years before that with rainfall? We really don't have a big piece, a big data point. We're still building on those records and updating those statistics. And we're going to see periods where we get more rain and periods where we get less rain. When it's raining a lot, we think, wow, it's never going to stop. Yeah, and when we go through a drought period, we're like, wow, is it ever going to rain again?
We talked a little bit about this in the seagrass episode about like changes in technology. Do you guys worry about increasing, like Scott, you mentioned, like we're collecting more data and we have these Doppler estimates now, these NextRad products. How do you account for the potential bias because there's just more data? That's just like the age-old argument about, are there more storms or not? Is it just because we're able to see them now, because we have satellites, which they didn't have 100 years ago?
That's really kind of an interesting question that you pose is, do we have too much data? And I think the answer for us as scientists and engineers is we never have enough data, right? We want more data. And I think if you kind of go back to, again, what is the problem? We're trying to understand, where does it flood? Yeah. And we're using models, and models are, in theory, trying to reproduce what's happening in reality. Yeah. And the better we get at our modeling, it's because we're closing that gap of what's theoretical and what's really happening in the world. And so the more details that we can add to the model, the better. But there becomes this point where it's just too much. It's too much of an effort. You don't really get the gains from adding more and more data. Yeah. So yes, it'd be great to have all that data, but we have to have the technology to be able to process all this data. Fortunately, the advancements in technology over the last 10 years have been pretty amazing. And it's allowed us to do a lot more things that we haven't been able to do in the past.
Yeah. When there is a storm that affects a lot of people, we know about it instantly too, with all the media that we have and the technology to be able to transfer information. Back 150 years ago, 100 years ago in Florida, they see the clouds rolling in and say, wow, I maybe better start walking up to higher ground. Yeah. And that was the most warning they had. They could see the birds flying a certain way. Yeah. And they say, let me go the way the birds are going.
If you're lucky enough to have a barometer or your left trick knee started hurting, that was it. It's time to head for the hills. Yeah. This is one of the things I really enjoy about working at the district is that, we're what makes us different from an academic institution is, they're focusing primarily on research-based questions. And while that's really important, we have to ultimately use the best available data we have to make decisions. Let's step back to you're getting ready to do a watershed management plan, right? Right. What's the first step? Like, how does this happen?
What you want to do first is pose the question, well, what is the purpose, right? What is the purpose of that study? And so the first question has been, where is it going to flood, right? But we might have some other type of goal in mind. And for our watershed management plans, what we're doing is that the ultimate use is to be able to have that information as best available information for our environmental resource permitting. They're able to use that information to make better decisions when they're looking at applications to be able to issue permits. Moving on to the second part, the mapping side of things, we want our results of these watershed management plans to be the best available information to update flood insurance rate maps. And so our governing board goes through the process of reviewing all of the work that we do as part of the watershed management plans. And when we're completed, they go through that review and approval process. And once approved, we then are allowing our cooperators, so it could be the cities and counties, to update those flood insurance rate maps with FEMA.
Mm-hmm. See, I think that's something a lot of people don't realize that we do, is that we really support that flood mapping process, and that directly relates to FEMA and to insurance. But do we do this alone, or do we typically partner up with local governments? How does that process work?
Yeah, so the local governments, the cities or the counties, will typically come to us first and say, hey, we want this information in our county. And what is this information? Well, it's just a very detailed look at the property level, each individual property, where you live, where Scott lives, where I live, to be able to know what is that flood risk or not. And so the city or county will come to us because maybe they're growing, or because maybe they just have lack of information or knowledge about the flood risk in that area. And then we will partner with them through our cooperative funding process, which Scott can probably define a little bit better.
Yeah, so our cooperative funding initiative is a cost share program that we have here at the district. And every year we open it up to our cooperators to submit applications on projects that we're interested in funding. And the watershed management plans are one of those types of projects that we fund through the cooperative funding initiative. And so typically the application will come in once a year. We'll evaluate it. If it is a good project, we'll rank it high and bring it back to our board with high recommendations to ask for funding, so it gets in our next year of budgeting.
Mm-hmm. And not every watershed within the district has a watershed management plan.
Correct. We've covered about 75% of our district, and just to put a scale to it, Chris. What we're talking about maybe a 40 or 50 or 60 square mile area. Which is a portion of a county. It's not even an entire county. Mm-hmm. Maybe each county has, maybe 8 or 10 or more different watersheds in them. And how we define a watershed that we're going to pick is it's going to be based on the topography. It's going to be based upon, is that water going to this lake? And so all the rain that hits this 40 square mile area, is it trying to get to this lake system, or is it trying to go to this river or this common low area? So we'll just take this area of land, and that's where we go in and we start gathering data and information to try to, as Scott said, replicate reality in our models.
Do you have, I imagine there's watersheds that go across counties. Like, that's one of the unique things. If you look at the boundary of the water management districts, they don't follow political boundaries. They follow watershed boundaries. And so what happens in that situation where, like, maybe a watershed, and I'm thinking like Peace River, do you subdivide that into smaller watersheds, or do you just go across different counties?
In the past, and it would depend maybe on some of the funding and things like that, we may have stopped at a county boundary, but these days, and really probably for the past 15 to 20 years, we look at where that topography is. So if it crosses into a different county, we're going to capture that, because what we're looking for is, when it rains, what are the contributing areas that are going to come to that spot? And if we just stop at a county boundary, we're neglecting a lot of contributing area. Our models aren't going to be be accurate. We're not going to get that flow that would come down into the watershed. So we don't necessarily stop it at a county boundary. We're going to look at where the actual edges and those ridges are.
And sometimes we don't even stop at the political boundaries. We're also making those connections between other watersheds, because all these watersheds are not closed basins, but they will flow to other watersheds as well. So you have to have that coordination between maybe two watershed models. And so that's something that is very important to understand. And I don't know if Mark's going to be able to talk a little bit about this, but the difference between open and closed basins is something that was significant when we were looking at the flooding in 2024. We saw a lot of closed basins flood.
Thanks for watching part 2 of our watershed management series.
Now stay tuned for part 3, where we will investigate what happens after flood events occur.